Let's see. Now, yeah, let's go to some symbols here, and then we'll run through a problem or two, a question or two. Okay, now it turns out that there are parallels or analogs between rotational terms, and linear terms. So, for example, we measure horizontal displacement as displacement, which is x, right? So if we were measuring along a line up here from 0 to 5, x equals 5, right? X is horizontal displacement. Well, in rotational terms, rotational displacement is, well, it's rotational displacement. I should just write that. Rotational displacement is, we use the symbol theta, which is the same symbol we use for an unknown angle, okay? So when we're talking about a circle here, we want to know how far the circle has gone around. Like if it's a rotating record, well, you don't know what a record is. If it's a rotating merry-go-round, and we want to know how far it's gone around, we can measure the rotational displacement in radians. So if it has gone this far, that is 1 radian. If it has gone all the way around, 1 full revolution, it would be 2 pi radians. Okay, so rotational displacement is theta, and it's analogous to linear displacement when we're talking straight line thing. Okay, velocity or speed is meters per second, okay, which is displacement divided by time. Rotational velocity is in radians per second. Okay? And those are analogous to each other. So if we have something walking along in a straight line, it goes 5 meters in 2 seconds, that'd be 2.5 meters per second, 5 meters in 2 seconds. And that's how fast something is moving in a straight line. Well, sometimes we want to know how quickly something is spinning. All right. So if the pen takes 1 second to go all the way around, then that would be 2 pi radians per second. Finally, we have acceleration, which, as you know, is a change in velocity, which would be meters per second squared for linear measurements. And for rotational units, rotational acceleration is radians per second squared. That's it. Okay, and this is, yeah, rotational displacement, it is in radians. Now symbols, yeah, that's the part I left out. Okay, so symbols. Now, as we know, for velocity, for linear velocity, V is the symbol, we know that. For rotational velocity, radians per second, we use omega, which looks sort of like a cursive W, okay? For acceleration, linear acceleration, we use lowercase a, as you know. For rotational acceleration, radians per second squared, we use the symbol alpha, which looks sort of like a fish. Okay, so to sum up, radians are, the symbol is theta, and the analogy is x, which is in meters for displacement. So we use meters for straight lines, radians for rotational, x for straight lines, theta for radians rotational displacement, which is how far something is turned. Linear velocity is v, meters per second. Rotational velocity is omega in radians per second. Acceleration straight line is A, meters per second squared. We already know that. But when we're talking about rotational acceleration, it's alpha and it's radians per second squared. And what rotational acceleration is how quickly the rotational velocity is changing. So if it's going slowly and then faster and faster and faster and spinning up very quickly, that means that there's a change in the rotational velocity, and we can hang a number on that. That's the rotational acceleration. Okay, now, like I say, next time I'm going to show you a group of equations which make it pretty easy to go from one of these to the other and are the reason that radians are so useful to us. Okay, finally here, let's see, how are we doing on time? We'll be okay. Let's look at a question here. So suppose we have a clock face, all right, and we are going to say that it is, I don't know, let's say it's 3:50. That's the time, okay? So we have our hours here, the 3's over here, 12's over here, 9's over here, 6. So we have the hour hand kind of below the 3 a little bit, down toward the 4, but the minute hand is pointing at the 10. Okay, so the time is 3:50, and the clock hands, we are interested in the minute hand because we want to know the rotational displacement of this minute hand. Okay, so we're going to find rotational displacement in radians. Okay, in radians. Now, your book uses the same convention that your math class does, calling the horizontal line here 0. Okay, that's 0. And this is the positive direction, positive. Okay, so our angular displacement here is 1, 2, 3, 4, 5 5/12ths of the whole circle. Okay, so 12 graduations in a clock face, and we are going from horizontal, which is what we consider 0, to the 10, which is 5/12ths of the way around the circle. And we want to know how many radians is that. Well, we have 5/12ths of a circle times 2 pi radians per circle, right? 5/12ths of a circle. Circles cancel, and we wind up with 5 times 2 times pi equals divided by 12 equals. That is wrong. Let's see. Yeah, fat fingered something there. Anyway, so it comes out to be 2.62 radians. Okay, that's the answer.